Hello, hello. Okay, so welcome back. We're going to talk about lesson 7.3. I'm at home this morning. My cat is meowing. Please ignore her. She needs attention. So we're going to talk about the normal model again, talking more specifically about z-scores and how to find probabilities that are more specific. So let's go and recap what we learned in the first lesson over 7.1 to 7.2, which went through the empirical rule. The empirical rule just tells us some basic percentages about what is happening between certain values on our normal model. And it's really good for finding percentages and finding values that are at a specific place. So if you remember, if I were to assume the heights of females are normally distributed, what percent of all females have a height that is between 1 and 2 standard deviations above the mean height or taller than the mean height? So I know that I'm talking about 1 standard deviation above the mean to 2 standard deviations above the mean. I can shade that area, and using my lovely empirical rule, I know that that answer is 13.5% because I've divided up all of those percentages. Right? I could also rephrase that question and say, what is the probability that an individual female will have a height that is between 1 and 2 standard deviations? That's the same thing. Probability is the same thing as the percentage of the area on our normal model. So I can phrase that question in two different ways, and it's the same thing. So still 13.5% or 0.135. Sorry, I had trouble there. But then I could also switch and talk about now heights of males and say, assume the heights of males are normally distributed. What percent of all males have a height that is between 1 and 2 standard deviations taller than the mean height? Will still be 13.5%. Now, for males, what is considered the mean and what is considered 1 and 2 standard deviations, those numbers are going to be different. But in terms of standard deviation or z-score, it's the same. So why are all these answers the same? Because when we use z-scores with a normal model, a z-score just represents how many standard deviations the number is away from the mean. Those z-scores kind of scale different units of measurement or different sets of data to the same units. And that's why it's all the same. And that's why the normal model is so useful in terms of finding probabilities. So where do z-scores come in? So let's say I was trying to find the percent of females whose heights are between 1.2 and 2.7 standard deviations above the mean. So that was their z-scores, 1.2 and 2.7 for those two individual heights. So that's kind of like from here to maybe about right there. And it's kind of hard to tell just using the empirical rule. I can surely estimate based on the percentages that I've labeled, but it's not going to be easy to tell an exact answer. It's actually probably not even really possible to find an exact answer. So that empirical rule is only going to help us find percentages when the z-scores of our values are exactly -3, -2, -1, 0, 1, 2, and 3. So I can only really use that empirical rule if we're talking about those specific values that land on those exact like z-score standard deviation places. So z-scores in and of themselves are helpful because they allow us to determine more specific percentages using any z-score along our x-axis, not just the whole number ones. So one way of doing this is using the z-table. And back in the olden days, I always say, before we had calculators and computer programs that could do lots of things like this for us, this is what statisticians of old used to have to do. Right? They used what we call a z-table. A z-table is basically a very large table of numbers. Basically, someone did all the calculations, and it actually involves calculus, of finding all of these little these percentage areas at each individual space along the z-table. So not just at the whole number standard deviation marks, but at every individual decimal place. And they put all of those numbers in this table, and we could use those tables to calculate areas. So just to kind of zoom in on a specific part of the table, I could use this table to find if I had a z-score of -2.73, I would know that the area to the left of that particular z-score of -2.73, and the area below that is 0.0032 or 0.32%. So I could use the z-table. But we're not going to do that because we have calculators and we have computer programs that can make things a lot quicker for us without having to go through all the trouble of looking things up on a table. So what we're going to use is a website. Now, there is a way to do this on our TI calculators, but since we're in a weird year, and I think it's a lot quicker and a lot simpler to use the website. That is what we're going to use. So there's a website, there's many websites that are out there. We're going to use one called from Statlet. It's the same kind of general website we've been using for lots of things this year, but it's statlet.com/normal.html. And what we are going to do is plug in our values. So let's go straight to an example and talk about how we use this website to calculate probabilities. So this problem says that the weights of newborn children in the United States vary according to the normal distribution with a mean of 7.5 pounds and a standard deviation of 1.25 pounds. So remember how I talked about in the last lesson, we talked about how in a normal model, the two numbers that are really important that we need to always pull out and figure out to start with are the mean and the standard deviation, right? With back when we did binomial in the last unit, the two numbers that were important with binomial were n and p. With normal model, the two numbers that we always need are the mean and the standard deviation. So in this example, this first part, we're going to find what the probability is that a newborn baby will weigh between 6 and 7 pounds. So I could label my normal model like we did in the last lesson, right? My mean is 7.5, and then I can add my standard deviation 3 times on the right, subtract it 3 times on the left, and I can get these values. And then if I want between 6 and 7 pounds, I can kind of shade or draw where that would be. There's about 6, there's about 7, and I know I want that area that's in between. And I could try to use my empirical rule to kind of estimate that looks like half of that area, and that looks like maybe a third of that area. And I could try to figure it out that way, but that's just a lot of work. And we can get a more exact answer by using a calculator website. So what I'm going to do is I'm going to go to the statlet.com/normal.html, and I'm first going to type in the mean and standard deviation for this particular problem. That's always going to be your first step. So I'm going to come over here where I've gone to this website. I'm going to click for mean and put 7.5, and I'm going to click for standard deviation and put 1.25, and I'm going to say plot distribution. So that will actually draw and label our normal model just like we did a second ago by ourselves. It doesn't put the percentages in each area like we did by ourselves, but it's there. So then the next step is on the drop-down menu that's below the graph, you have the option to calculate the area between two values, to the left of a value, to the right of a value, or outside a region. So for this problem, because we want between 6 and 7, I'm going to click between two values. Then I'm going to put in my 6 as the left boundary and 7 as the right boundary, because that'll give me the area between the two values. So I'm going to say left boundary 6, right boundary 7. I'm going to say calculate area, and voila, it will give you the area that is between those two values. And it even shades it on the graph for us, which is really, really handy. So now we know that the area between those two values is 0.2295, which is 22.95%. So about 22.95% of newborn children will weigh between 6 and 7 pounds when they are born. One thing I did want to mention, I'm not actually sure if my calculator is doing this by default, but one thing that I figured out, and this worked with binomial too, there's this link down here that says adjust color, rounding, and percent proportion preferences. So if yours is giving you a percentage and you want it to give you a proportion, you can change that or go back and forth when we, in this top section that says rounding display of proportions. So you can kind of pick whether you want the answers to be given to you as percentages, or if you want the answers to be given to you as decimals or proportions. You can also pick how many digits you want it to round to. I'm going to keep mine at decimals and 4 decimal places because that's where I had it. If you also wanted to, you could change the color of your shading. That's extra. And then at the very bottom here, make sure that you put done so that it actually saves that. And now when you calculate areas, it'll use your preferences. So I just wanted to mention that in case yours is not giving you the decimal version automatically, you can change that. Or if you wanted a percentage, you could change it to percentage. So that is how we do a between. So let's do another one, still dealing with the newborn children. So we have the same X values. And now we want to know what percent of babies weigh more than 10.25 pounds at birth. So we're going to start again. There's my shaded region. If I were to do this by hand, by drawing it out, 10.25 is a little bit above 10, and then we want more than that, so I shade to the right. So I can see this very teeny tiny area. I get an idea that it should be a pretty small percentage or proportion. So again, I'm going to statplot.com/normal. I already put my mean and standard deviation in, so I don't have to do that again. I could re-click plot distribution if I want that to clear out. And then this time I want greater than, I want more than 10.25. So on an x-axis, greater than is going to be to the right of a value. So I'm going to make sure my little drop-down menu says to the right of a value. And then I want that value to be 10.25. So I'm going to type that in under value and say calculate area. And then it shades it for me and it gives me the area as a proportion. Now this particular question asks for a percentage. So I could just take that number and multiply by 100 to make it a percentage. Or if I really wanted to, I could change my options to percentage and then click calculate area again, and it'll give it to me as a percentage. So it's totally up to you how you do that, but you can kind of switch back and forth and change back and forth what you need. So when we do that, like I said, we get 0.0139 or 1.39%. So about 1.39% of babies weigh more than 10.25 pounds at birth. And then similarly, I could do a less than percentage by using the same calculator. So if I wanted what's the probability that a baby weighs less than 5.5 pounds at birth, if I were to use my model and shade, there's where 5.5 would land, and we want less than. So you can get an estimation. But if I use my lovely little calculator, I'm going to say this time, and you can plot distribution again to clear it out. This time I want to the left of a value, and I want that value to be 5 or 5.5. Yeah, 5.5. And then calculate area, it shades it for you, and then it gives you the area as a decimal or percentage, whatever you checked your options as. So we get an area of 0.0548 or 5.48% when we do that. So that is a less than value. The other thing we can do with our calculator is to kind of work backwards. So this is where instead of giving you a value and asking you for a percentage, either between two values less than or more than, this time we're given a percentage and asked for what value would give me that percentage. So for example, with the baby weights, I could answer how heavy must a baby be to be in the top 2.5% of baby weights. So I want the baby to weigh the top 2.5% when they are born. So one way to do that would be to literally kind of estimate by looking at my percentages, and I'm trying to get 2.5% at the very top of the graph. So I could sit here and add, well, 0.15 plus 2.35 is 2.5, so probably at about 10 or more would be my top 2.5%. So I could estimate and get pretty close to the answer using that. Not always going to be that simple. This one was really nice, but we can also use our calculator to get that same general answer. And actually, our calculator will give us a much more exact answer. So this time, when we use our calculator up here, we're going to go to the very top, the very, very top where it says operation, and I'm going to change that to, instead of calculating an area, I'm now calculating a value that corresponds to an area. So I'm going to switch it to that. I still have the same mean and standard deviation because I'm still dealing with the baby weights. So I'll just say plot distribution. And now you have a new kind of set of things down here below the graph. So what we're going to do next is, we already did the plot distribution. Below the graph, since we want the top 2.5%, I'm going to change this little drop-down menu to say the right tail area. Right? Right tail would be the upper whatever percent, left tail would be the lower whatever percent. So since we want the top 2.5%, I'm going to say right tail. Now this is the only thing you have to be careful of. This particular calculation, using that calculator, only wants proportions. You can't type in. If I try to type 2.5, it's going to say no, it has to be like a proportion. So we do have to type in here as a proportion. So if you're forgetting how to do that, to turn a percentage into a decimal, you just divide by 100. So if I did 2.5 divided by 100, I would get 0.025. So that's what I'm going to type in here, 0.025. Then I say calculate area, and it tells me the value that we're at. We estimated 10-ish by using the kind of our empirical rule percentages. The actual value is 9.95, so we're pretty close by estimating. So that means that babies who weigh 9.95 pounds and above at birth are the top 2.5% of baby weights. So that's how we can use our calculator to go backwards. So let's do one last example that puts everything together and just practices everything at one time. So this one's talking about IQ scores. So IQ test is just a measure of kind of natural intelligence as opposed to what you know. It's more like how your brain works. So IQ scores are normally distributed with a mean of 100 points and a standard deviation of 15 points. So I could start by having my normal model and labeling my mean and then going out standard deviations in either direction. My cat is really close to the computer right now, so if you heard her very loudly, that is why. So we're going to go through and answer some questions. So first question is, what percent of people have an IQ that is between 120 and 130? So what I'm going to do is I'm going to go to my calculator. I'm going to click at the top back to I'm calculating an area under the normal curve. So when you were asked for a percentage, what percent of people, what is the probability of, blah, 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 we are calculating an area. So that's kind of one thing to look for. When I'm looking for a percentage or a probability, I'm calculating an area. So I'm going to say calculate an area, and then I'm going to change my mean to 100 and my standard deviation to 15, and then click plot distribution. And now I have this lovely labeled graph, just like we did a minute ago. And then I want between 120 and 130. So I'm going to say between two values, 120, 130, and then calculate area. We get an area of 0.0685, which would be 6.85%. So 0.0685 is 6.85%. The next question says, what is the probability that a person has an IQ that is higher than 140, which would qualify as genius? So for this one, I'm still going to be calculating an area because I'm asking for a probability, so I don't have to change that up there. And then this time I want greater than, so I'm going to say to the right of a value, and then I'm going to change that value to 140 because I want greater than 140. Calculate area, and then it gives me that area. So there it is shaded as well, but my area is 0.0038 or 0.38%. So only 0.38%, less than a percent, less than half a percent of people have an IQ that is higher than 140. The third question says, what IQ would you have to be in the top 10%? So this is one where we are using our thing backwards. This time we have a percent and we're looking for an actual IQ value. So that is when we switch it to calculate a value corresponding to an area, right? You can think of a value is a number on the x-axis. An area is a percentage or a probability. So those are things, if you're having trouble remembering which operation do I use, maybe write down in your notes, say value is x-axis number, area is percentage or probability, and that might help. We still have the same mean and standard deviation, and then this time we want the top 10%, so I'm going to say right tail, and then I'm going to change that to 10%. 10 divided by 100 would be 0.1, and then calculate value, and it tells me that that value that marks off the top 10% is 119.223. So that means that an IQ score of 119.223 or higher gives me the top 10% of IQs, the top 10% of natural intelligence. And then the last question we're going to do is, what interval represents the central 75% of IQ scores? So interval means I should be getting two numbers. I want to know what two IQs have an area between them that is 75% on the graph. And I do want the middle 75%, so I know I'm going to be in the middle. So the way I do this on my calculator, I'm still calculating a value because I have a percentage and I want to know what the values are that lead to that percentage. And then I want this time the central, and then I want 75%. 75 divided by 100 is 0.75. And then I'm going to calculate the value, and it tells me the left and the right, like, area, interval, number that would mark off that area. So 82.745 to 117.255. So IQs between those two numbers represent the middle or the central 75%. So 75% of people have IQs between 82.7 and 117.255. So that is pretty much it. That's how we use our calculator. Just like with binomial, once you kind of know the tricks of how to use the website, it makes answering these questions a lot simpler. If we had to go back, if you remember I showed you that Z table, if I had to use this Z table to find all of my probabilities, it would take me a lot more time. So that is how we do that. Thanks, guys. Have a good day.